Okay, welcome to Chapter 10 from our physics class. We're going to be talking about fluids. So, what defines a fluid is that its ability to flow. So, there are three common phases of matter. There are solid, liquid, and gas. And I think we probably tend to think of liquids as being fluids, but we may not be considering the fact that gases are also fluids. Gases flow, air flows. That's basically what wind is flowing air. And so any of these two phases, liquid or gases that do not have a defined shape, that are able to flow and fill the and take the shape of a container, are fluids. So liquids tend to have a fixed volume. It's very difficult to compress liquids. But gases, they can flow and they can be compressed with the application of pressure. They can be compressed to change their volume. So that's one of the primary differences in the behavior of liquids and gases, is the ability to compress them. So one of the key characteristics of a fluid that we need to become familiar with is its density. So we're going to use this symbol here of rho to indicate density. This is the Greek letter rho. And let me turn on my pen here so I can just kind of highlight a few things. So there we go. Rho is equal to mass over volume. So essentially density is just telling us how much stuff we have, how much mass there is, divided by how much space it takes up, or what the volume is. So our units of density are going to be kilograms per meter cubed. Water, by the way, at approximately 4 degrees Celsius, which is just above freezing, so we are talking about water here, not ice, has a density of 1 gram per cubic centimeter, which is equivalent to 1,000 kilograms per cubic meter. So that's sort of a useful piece of information to make note of. That's going to bring us, we'll get to it in a moment, the idea of specific gravity. But first, let's look at an example problem here. So if we have an iron wrecking ball that has a radius of 18 centimeters and it's made of solid iron, what is its mass? How massive is this? Well, we need to be able to, first of all, calculate what is the volume of a sphere. So if you don't know off the top of your head, you can look up from any number of resources the formula for a volume of a sphere and find that it is equal to 4/3 times pi r cubed. So if we take 4/3 times pi times our radius, which is given to us as 18 centimeters. Now, we would like to use meters. That's our standard unit of length. So converting that to meters, we just have to move that decimal place 2 times, and this becomes 0.18 meters cubed. Okay, so 4/3 pi times 0.18 cubed gives us 0. That's 0.024 cubic meters. So we know the volume. How are we going to find the mass? Well, the density is, again, something that we can look up. We're dealing with solid iron here. So if you actually look up in table 10.1 of your textbook, you'll see that the density of iron is 7,800 kilograms per cubic meter. And so if density is equal to mass divided by volume, and we want to know the mass, then mass is equal to density times volume. So we take our density, which we looked up in table 10.1, 7,800 kilograms per cubic meter, and we multiply that by the volume, which we calculated in the first step, 0.024 cubic meters. We find that we have a mass of 190 kilograms. So that's just a fairly straightforward example problem demonstrating the relationship between mass, volume, and density. So I mentioned earlier that the density of water is 1,000 kilograms per cubic meter. And that leads us to this idea of specific gravity. It's often useful to compare the density of other substances to that of water. Water's sort of a benchmark here. So if we took the density of some material here and divided it by the density of water, which is 1,000 kilograms per meter cubed, and got 11.3, we would say that the specific gravity of that material is 11.3. So we'll come back to that idea of specific gravity in a little bit. Let's move on to the concept of pressure. So pressure is something that fluids exert on their surroundings, and also on objects that are submerged in that fluid. So here we have a container of water. It is exerting a pressure against the sides of the container, and we have a little tiny cube here in the center of the fluid. It has pressure acting on it from all sides. And the thing is that the deeper into the fluid you go, the more of that fluid is sitting on top of you, and so the greater that pressure gets. If we were to actually draw a diagram of the pressure acting on the sides of this container, it increases with depth. So at the very top, there's very little. Actually, at the very top, there's no pressure. And then the deeper you go, the more and more pressure is exerted along the side of that container. So the fluid is exerting pressure, and the units of pressure in the metric system are the pascals, which is equal to 1 Newton per meter squared. There's a joke I would normally tell in class about pascals and Newton per meter squared, but I don't know that it'll work well via video. It generally works better in person. So hopefully I'll be seeing you guys again in person sometime soon, and I'll be able to tell you my Pascal joke. So the thing about that pressure that the fluids exert on the containers that they're held within is that pressure is always perpendicular to the surface of the solid. There's no pressure acting up. Otherwise, the pressure would cause the fluid to just jump right out of the container, and obviously it doesn't do that. So fluid at rest exerts pressure in such a way that pressure is perpendicular to the surface. As I mentioned, the deeper into a fluid you go, the more pressure the fluid exerts. And so we can come up with a formula for that here, and it is equal to P, pressure, equals rho GH, where rho is density, G is the acceleration due to gravity, and H is the height below the surface of the fluid. So this is true for any fluid, any homogeneous fluid whose density doesn't change. So assuming the density is constant, then the deeper you go below the surface, the greater the pressure becomes. And at any depth h, we can calculate what that pressure would be using rho GH. Let's take a look at an example problem here where we have water that is in a water tower. This is commonly used to create pressure in water pipes by raising the reservoir of water up above the spigot and allowing gravity to pressurize the system. So if we have a storage tank that is 30 meters above the level of the faucet, so there's a faucet here inside the house, and we want to know what the pressure is there, we can calculate that using our delta P equals rho GH. The difference in pressure is equal to rho GH. And so the density of water, again, is 1,000 kilograms per cubic meter. Acceleration due to gravity is 9.8 meters per second squared. And in this case, the height, the change in height from the level of the water in the storage tower to the faucet is 30 meters. So rho times G times H gives us a pressure difference of 2.9 times 10 to the fifth. And this is newtons per meter squared, and a newton over a meter squared is equal to a Pascal. So this is 2.9 times 10 to the fifth pascals is the pressure in the water. So this is true of any fluid, as I said. Remember that air is also a fluid. So we are, as we all are on the surface of the Earth, have the entire atmosphere of the Earth on top of us. And that air, that fluid, is exerting a pressure on us at all times. At sea level, the pressure is approximately 1 atmosphere. 1 ATM or atmosphere is a unit of pressure, which is equivalent to 1.013 times 10 to the fifth newtons per meter squared, or in other words, 101.3 kilopascals. This is the atmospheric pressure that we experience all the time. This is 1 ATM. Now, of course, atmospheric pressure changes with changes in the weather. That's why we have barometers that measure barometric pressure. But roughly, the average pressure is 101.3 kilopascals. Yet another unit of pressure is the bar. 1 bar is equal to 1 times 10 to the fifth newtons per square meter, or 1 times 10 to the fifth pascals. Okay, and the reason why all of this pressure acting on us doesn't crush us is because we're accustomed to it. The cells in our bodies have an internal pressure that's pushing out. So in all our little bodily cells, we have pressure pushing out, the atmospheric pressure is pushing in, and those two pressures are equivalent to each other. Now, if you've ever driven through the mountains or gone on an airplane flight and felt your ears pop, that's because you are experiencing a change in that pressure, and your body has to adjust to it. So the higher up you go in elevation, the less air you have on top of you, and therefore the less the external pressure is. I think I'm going to stop right here, and we'll pick up talking about gauge pressure in the next video.